So analysis of variance, last section of chapter 10, last section of senior year. An analysis of variance is used to determine if a difference exists between mean times, for example. When only one variable is being studied, the process is called a one-way analysis of variance. One-way analysis of variance is a hypothesis testing technique that's used to compare the means of 3 or more populations. Analysis of variance is usually abbreviated as ANOVA. Null and alternative hypotheses are going to be similar to your H sub O being all your means equal to each other, and then H sub A being that at least one mean is different from the others. So in order to perform a one-way ANOVA test, these conditions have to be met. Each of the K samples, where K is greater than or equal to 3, must be randomly selected from a normal or approximately normal population. The samples must be independent from each other, and each population must have the same variance. If these conditions are met, then sampling distribution for the test is approximated by the F distribution. So we're still using those F tables. Your test statistic is F equals MS sub B over MS sub W, which we'll get to shortly. Your degree of freedoms are K minus 1 for your numerator degree of freedom and N minus K for your denominator degree of freedom, where K is the number of samples and N is the sum of your sample sizes. So all your samples sizes added together for every category or every sample is going to be your N value, your capital N value. One other way to look at your test statistic is to say that F is equal to the variance between your samples over the variance within your samples. So finding the test statistic for a one-way ANOVA test, you're going to find the mean and the variance of every sample. You're going to find the mean of all the entries in the sample, or the grand mean, which is denoted by X double bar. And you find that by adding up every X value and dividing it by the total of all the samples added together. You're going to find the sum of the squares between the samples, which is SSB. You're going to find the sum of the squares within the samples, which is SSW. And then you're going to find the variance between the samples, which is that MS sub B that I mentioned just a minute ago. So to find that, you're going to take SSB from step 3 and divide it by your degree of freedom from the numerator. And to find the variance within the samples, to find that MS sub W I mentioned, you're going to take SSW from step 4 and divide it by your degree of freedom for your denominator. You're going to take those two values in 5 and 6 and divide them in number 7 to find your test statistic F. Now when you're finding SSB and SSW, you're coming down here and looking at these general formulas. So SSB is going to be your sample size from sample 1 times mean 1 minus your grand mean squared plus sample size 2 times mean 2 minus grand mean squared, so on until you get to that last sample. And then SSW is sample 1 minus 1 times your variance from your sample 1 plus sample 2 minus 1 times your variance from sample 2, so on until you get to your last sample. Your steps for performing a one-way ANOVA test: you're going to verify the samples are random and independent, the populations have a normal distribution, and the population variances are equal. You're going to identify the claim and state your hypotheses. Make sure you know your level of significance. Find your degree of freedom for the numerator and denominator. Find your critical value, rejection region, test statistic, reject or fail to reject, and interpret in context of the original claim. So, in other words, exactly the same that we've done this chapter, in chapter 8, and in chapter 7. Okay, so in number 1, a sales analyst wants to determine whether there is a difference in the mean monthly sales of a company's 4 sales regions. Several salespersons from each region are randomly selected and they provide their sales amounts in thousands of dollars for the previous month. The results are shown in the table. At alpha equals 0.05, can the analysis conclude that there is a difference in the mean monthly sales among the sales regions? Assume each population of the sales is normally distributed and that the population variances are equal. So we have 4 regions. So when we write our HO, it's going to be that the means are all equal. And HA is going to be that at least one mean is different. And they are asking that if the analysis can conclude that there's a difference in the mean monthly sales of the sales region. So if there's a difference. So HA is our claim. So I already gave you guys your sample sizes, your means, and your variances for each of the regions so that we wouldn't have to waste time doing that ourselves. What we need to find is we need to find critical values, rejection region, the grand mean, and then we'll have to find SSB and SSW so that we can find MSB and MSW in order to find our test statistic. So these are a little bit more work. It's not so much that they're hard, but you just don't want to end up making a silly mistake. So you want to just make sure you're paying attention to everything. So our degree of freedom for our numerator is K minus 1, which in this case would be how many different samples we had. So 4 minus 1, which would be 3. Our degree of freedom for our denominator is N minus K, so that's at capital N. So we have 4, 5, 4, and 5, which is going to give us a total of 18 in all of our samples. So 18 minus the total different samples, which is 4. So it's going to be 14. So when we find our critical value, we're going to look up 0.05 on the table for alpha, and we're going to go over to 3 for our numerator degree of freedom and down to 14 for our denominator degree of freedom, which is going to give us 3.34. And remember, these are always right-tailed, so we want to be greater than that for our rejection region. So I'm going to find our grand mean. I do that by totaling all of our samples. So 34 plus 28 plus 18 plus 24 plus 47 plus 36 and so on for all 4 of those different regions, which is going to add to 574. And I'm going to divide that by 18, which was my capital N value. So when I divide those, I get 31.8 repeating, and I'm going to round that to 3 decimals, so 0.889 for my grand mean. So now I have to find SSB. So when we find SSB, we are doing our sample size times the mean of that sample minus the grand mean squared for every single one of those. So for the north, my sample size is 4 times the mean of 26 minus the grand mean squared. And I'm going to do that for all 4 of those. So when I square each of those and multiply it by the sample size, add them all together, I end up with 549.778. So next I'm going to find SSW. So when I'm finding SSW, I'm doing the sample size minus 1 times the variance for each of these. So 4 minus 1 is 3 times the variance of 45.33 plus 5 minus 1 times the variance of 45 plus 4 minus 1 times the variance of 40.67 plus 5 minus 1 times a variance of 42.5. So when I multiply and add all of those together, I get 608. So now I'm ready to find MSW and MSB. So for MSB, it is my SSB divided by the degree of freedom of my numerator. So 549.778 over 3, which is going to give me 183.259. And then MSW is going to be SSW, which was 608, divided by my degree of freedom of my denominator of 14, which gives me 43.429. And then I use those two values to find F. And when I divide those, I get 4.220 or 4.22, which is greater than 3.34. So I can reject my null hypothesis. And then my interpretation is just enough evidence to support the claim that the mean monthly sales among regions will differ. So probably a little bit more work in terms of how much we have to show and all of that than in the last hypothesis test, but hopefully not too much harder. Okay, so one more. Data shown in the table represents GPAs of randomly selected high school students. Alpha equals 0.05. Can you conclude that there's a difference in the mean of the GPAs? Assume populations of GPAs is normally distributed and variances are equal. So we've got freshmen, sophomores, juniors, and seniors, and the GPAs. So I'm going to go ahead and give you all of the values so that we don't have to spend time doing them ourselves. So for the freshmen, N was 7. The mean is 2.69. And the variance is 0.220. Sophomores, we had 10. We had a mean of 3.06 and a variance of 0.132. For juniors, we had a sample of 9, an X-bar, a mean of 2.74, and a variance of 1.47, or 0.147, sorry. And then seniors, we had a sample size of 8, a mean of 2.96, and a variance of 0.115. So HO is going to be that the means are all equal. HA, at least one mean differs, which is our claim. So our degree of freedom for our numerator, we have 4 classes minus 1 is going to give us 3. Our degree of freedom for our denominator, we had a total sample of 34 minus the 4 groups. So we got 30. So when we look up our critical value, 0.05 over to 3 down to 30, 2.92. So we want to be greater than that. When we find our grand mean, the sum of all of those GPAs is 98.77 divided by 34 gives us 2.905. So now we start the tedious work. So when we do SSB, we've got 7 times 2.69 minus 2.905 squared plus 10 times 3.06 minus 2.905 squared plus 9 times 2.74 minus 2.905 squared plus 8 times 2.96 minus 2.905 squared. And when we work all of that out, you should end up with about 0.833. And then SSW, we've got 6 times 0.220 plus 9 times 0.132 plus 8 times 0.147 plus 7 times 0.115, which gives us about 4.489. Now we're going to use those to find MSB and MSW. So MSB, we're going to take that 0.88833 and divide it by our numerator, degree of freedom of 3, which gives us about 0.278. And then MSW, we're going to take SSW and divide it by our denominator, degree of freedom of 30, which gives us about 0.150. And then to find F, we're going to divide those two, which gives us about 1.853 or 1.85, which is not greater than 2.92. So we're going to fail to reject HO, which means we do not have enough evidence to support the claim that there is a difference in the mean of GPAs. Okay, that was your last section, which means your last homework assignment is on page 565, 2 through 14 even. If you have questions, get on Google Meet, email me, text me, let me know.